great pleasure, an honor for me to be there. I already visited Japan. I have been extremely happy with the time I have spent in Japan. I'm very happy to be back in Japan, and especially here in Kyoto. This is the first time I visit Kyoto, which I think is even more fascinating than other cities in Japan. So everything here is very pleasant. Even the seminar room is very pleasant. Okay, so I want to talk about Langlands' comparability principle, which is a problem in, let's say, another theory. But the approach I want to introduce, to explain, is in fact analytic minded, and as you see by the titles of the different parts I have already written on the blackboard, I will be mainly concerned with Fourier analysis. So first I will begin with very classical Fourier analysis as it has existed ever since the 19th century. And then I want to explain that an equivalent way to talk about Langlands' comparability principle is to try to generalize this Fourier analysis in a setting which is both non-commutative and non-additive. So I will explain a little later what I mean. So I begin with the first part. So the first part is the very classical Fourier transform. So the Fourier transform is defined for functions over some space. We will immediately precise which type of spaces we consider. So how is it defined? It is defined by a formula which has the following form. So the Fourier transform of some function h is an integral with respect to a measure dt of h of t, and here you have some characters, some additive character psi of tt prime. So I want to make precise the data in this formula. So first here you have a measure. So I want this measure here to be invariant with respect to addition. Okay, so in fact this is the first appearance of addition in this formula, the first reference to addition. Secondly, I want this to be an additive character. So what does it mean? It means first it has to go to the circle. The circle is the group of non-zero complex number whose modulo is 1, of course, together with the addition, with multiplication. And here I want it to be defined on some space endowed with addition. Okay, so it has to transform addition into multiplication. So this, you see that in this formula, addition appears twice. It appears here with the choice of some character, and it appears there with the choice of some measure which is invariant with respect to addition. So, of course, here I want to iterate upon some space A. So this means
additive means that measure t is no complexity, or can you?
No, so t will be a variable belonging to the space A, and here this also belongs to A. So what can be A? A, of course, the most classical Fourier transform is for R, the group R, topological group R, endowed with addition. But it can also be C, also endowed with addition, and there it means that on C you have to choose some additive character, which of course is non-trivial. non-trivial character. But because this formula makes sense in some extremely general setting, it just the only thing you need is these things to be defined on some space with an additive structure. You want integration, so it has to be locally compact. So that you can talk about an invariant R measure. Okay, so you need addition on the local compactness. So this means that there are many possibilities. So as we are concerned with number theory, it can also be the field of p-adic numbers or a finite extension, a so-called p-adic field. And it can also be a so-called local field, which is the field of Laurent series with some coefficients in a finite field. So this is really for number theorists or algebraic geometers. And lastly, and very importantly for us, it can also be the Adel ring of so the so-called Adel ring of F, a global field. So a global field may be a Q or a finite extension of Q, or so a global field, so Q, or a finite extension of Q, or it can also be the field of rational functions with coefficients in some finite field FQ, or a finite extension of that. Okay, so these are the different possibilities, and in all these different contexts, and in fact, you can also find other contexts where it is possible to define the Fourier transform according to this formula. And then what I want to list on the blackboard are the main properties of the Fourier transforms. So I am going to write very basic things, but which in fact are extremely important. And these basic properties of the Fourier transform are what we would want, in fact, to generalize in the non-additive or non-commutative setting, which I will explain later. And I want to say that if we were able to do that, in fact, it would be equivalent to the Langlands automorphic transfer, which is a very deep result, or a very deep statement in number theory. So, there are, in fact, three very important series of properties for the Fourier transform. So the first thing is that this thing, the Fourier transform operator, is unitary. So unitary means that it respects the usual Hermitian product. So this means we are considering functions with values in C. So the Hermitian product is given by the integral over our space A with respect to the same additive measure of H1 of T, H2 of T bar. Okay, so it has to be a unitary operator. And not only that, but it has to induce an automorphism of the associated Hilbert space, which is the space of square integrable functions on our space A. Okay, so this is the second very important property. And of course, as we say, it is an automorphism, it has an inverse, and the inverse of this operator is the following. In fact, it is the Fourier transform itself composed with the map which associates to any element t its opposite, minus t. Okay, so the composite of the Fourier transform with this very simple change of variables. So this is the first the first family of properties of the Fourier transform, which in fact are extremely important and useful in analysis. So the second type of property is the following. This is what happens when you consider the multiplicative structure of the field of ring A. So this is the action of multiplication. So you see that in the definition of the Fourier transform, multiplication appears here. You are considering the image by psi of the product Tt prime. So the multiplication is there. And what does it mean, the action of multiplication? It means that if we have such a function on this space, then we can associate to it its translates, okay, by some invertible element of our field of ring. So what is this function? So this is a notation I introduce. So it is just the function deduced from H by right translation. Okay. So what can we say in general? Just by a formal computation of the formula which defines the Fourier transform, we can say the following. We can say that the Fourier transform of the function h translated by t is the same thing as the Fourier transform of h translated by t minus 1, but here there is a correcting factor. You have to take t, and here there is some absolute value to the power minus 1. So what is this? So this here, so this is multiplicative homomorphism from A cross to R plus cross. And how is it defined? It is a character through which A cross acts on additive measure. Additive measures. So remind you that when you have a locally compact abelian group, as we have here, the R measures, the measures which are invariant by additive translation, form a one-dimensional space. Okay? So when you consider such a measure and you transform it by the action of multiplication, you get another additive measure, and it is deduced from the previous one by multiplication by a scalar. So in this way, you define a character on A cross acting on the space of on the one-dimensional space of additive measures, and this character is denoted in this way. In fact, in general, it is a norm. So, for instance, in the case of R, it is the usual absolute value. In the case of C, because C is two-dimensional over R, it is the usual modulus elevated to the square. And in the case of p-adic fields, it is the usual p-adic norm. In the case of the Adel ring, it is the usual global norm, which is a product of all the norms at the local places. Okay, so this is the second type of properties we have. Then the third type, which is also very important, is the fact that it is. So here we have said the first property is that the Fourier transform defines an automorphism of the space of square integrable functions, but this space is huge. In some sense, it is too big. So the third property consists in saying that it is possible to define small spaces of, let's say, very regular functions from A to C, and I want these spaces to be stable under the following. So first, I want them to be stable under the Fourier transform, okay, and of course also under its inverse. Okay, its inverse is just a change of variable x minus t minus t, so it just means that this space is stable under this change of variable isomorphism. Okay, so it has to be stable under this, and I also want it to be stable under multiplication, which means I want it to be stable under multiplicative translation. Okay, so in fact it is possible to define in the huge space of square integrable functions some much smaller spaces which are stable under the Fourier transform and also under multiplicative translation. So how is it possible to do that? So there are several cases to be studied. So first, in the case of R, what do? You consider the usual Gauss function, and of course, a basic result of analysis is the fact that the Fourier transform of the Gauss function is itself. So, in order to define a space which is stable under the Fourier transform and multiplicative translation, what you can do is to add to the one-dimensional space induced by this function, you add the other spaces induced by the translates of this function. So this means that here you just modify the coefficient. Instead of minus t to the square, you have minus some positive coefficient t to the square. So this is in the R dimensional case. So in fact, number theorists are also used to. They also want spaces which are stable under invariant differential operators. So this means that here we also allow functions which are of this form multiplied by some polynomial in T. Okay. By now, in the case of C, you just deduce the case of C of the case of R using the fact that C is isomorphic to R to the square as a group. Then there are the case of non-Archimedean local fields. So these are the two cases. So these cases, I usually denote them Fx, are the localization of a global field at a so-called finite place. So here, what you consider is the space of functions from Fx to C, which have compact support and which are locally constant. Okay, so this is non-trivial because at non-Archimedean places, at finite places, the completion Fx is so-called totally discontinuous. So functions may be locally constant without being constant. Okay, and it happens that this space is stable under the Fourier transform, and of course it is also stable under multiplicative translation. Okay, and you can, when you know these cases, you can also deduce in general a definition of small spaces of very regular functions stable under the Fourier transform on the Adel ring. Okay, so this is the third property, and the last property I want to talk about is the Poisson formula. So, of course, I suppose that everybody knows the Poisson formula in the case of R. So what do? You have chosen, so this is the case when A is R. Okay, and then you have chosen this character from A to C, and you suppose here that the kernel of this character is Z, and the formula you have is the fact that the sum over the element of this kernel of some function of this space, the space we just talked about, evaluated at these integers, it is equal to the same expression evaluated for the Fourier transform. Okay, so this means that we have a discrete linear functional defined on these spaces of very regular functions which are invariant under the Fourier transform. So this is the case of
Poisson, the complexity is just constant?
Excuse me?
In the case of the Poisson, normally in the case of my analogy to the probability theory,
yes.
Poisson distribution is a kind of a little bit skewed binomial, which means
I don't think it is related, so you can go ahead.
Okay. So okay, so this is in the case A equals R. The second case, which is of interest to us, is the case of the Adel ring of a global field. In fact, this case is very analogous to this one, because it is a basic fact of number theory that F itself is embedded into AF, which is a continuous topological additive group. It is embedded as a discrete subgroup. So this is discrete, and the quotient AF divided by F is compact. Okay, and here you require the character you have chosen, the character psi you have chosen for AF, to factorize through this quotient. So you require this character to be trivial on the discrete group F. This is the only requirement you ask. You see that F inside AF has the same formal properties as Z inside R. It is discrete and the quotient is compact. And so, maybe it is not a total surprise that the sum over the element of this field of H evaluated at this element is equal to the same where you replace H by its Fourier transform. Okay? And this is formally the same Poisson formula, and it happens that this formula has very important and deep consequences in number theory, because this has been proved by Tate, but maybe in fact it has been discovered independently by Iwasawa. I'm not completely sure. So it was done at least in the thesis of Tate, that we have such a formula, and it induces usual global properties of so-called L functions of characters, automorphic characters of global fields. So how is it done? So you take this formula and you let the group AF cross act on it. What does it mean? It means that for any function h, you can consider it translate by an arbitrary element of AF cross. Okay? And you know that if you replace h by such a translate, then the Fourier transform here is replaced by its translate by the inverse of the element you consider, up to some correcting factor, which is written here. So you use this formula for all possible elements here. You observe, of course, that if you consider an element of F cross, this expression is not changed. So this means that, in fact, you have an expression of this quotient, which is the so-called automorphic quotient in number theory. So this quotient group acts multiplicatively on this formula, and so it has a meaning to decompose it spectrally. Okay? You have an identity, you have a group acting on this identity, and so you can decompose this identity according to all possible representations, irreducible representations. Here they are characters because you are considering an additive group, a commutative group. And what you get is the usual properties of global L functions, which means analytic continuation and functional equation. Okay, so this is the general scheme which had been introduced by Tate. And by now, what I want to talk about is how this can be possibly generalized. First, in the non-commutative setting, so this has been done many decades ago by Bodman and Jacquet, and then to non-additive setting, and this is really what I want to talk about. Okay, so what first? So I want to talk about the non-commutative setting. So what does it mean? It means that here I want to replace the space A by the space of matrices, R cross R matrices, for an arbitrary integer R. So this means that A does not change, but I replace the space on the functions are defined by these spaces. So you see that, of course, R cross R matrices still have an additive structure. So this formula does not need to be changed, except that here what you do is to replace psi evaluated at tt prime as you just take the trace of the product of the true matrices. Okay, so the trace of a matrix is a scalar, an element of A, and here you are still with an additive character of A. So, okay, so by now this formula makes sense, exactly the same way as before. And by now, let's look at the properties we had in the first case of the first commutative case. Let's see what they become. So first, here I have an operator. Is it still unitary? So the answer is yes, it is still unitary. It still respects this Hermitian product, which by now is defined over this space. And it still induces an automorphism of the space of square integrable functions on our bigger space LR of A. And its inverse is still given by the same formula. The inverse of the Fourier transform is the Fourier transform composed with this very simple change of variable. You change the variable t to minus 2. So then you have to look at the action of multiplication. So here you see you are with MR of L. So what is the natural group of MR of L? Of course, it is MR of A is an algebra, so the natural group is the group of its invertible element. So this means that by now we are considering not an element of A cross, but an element of GLR of A. Of course, GLR of A is no more a commutative group, and this is why I am saying that the second part, in the second part we are considering a Fourier transform which is still additive, because here we still have addition, but it is no more commutative. I am talking about non-commutative additive Fourier transform. Okay, so by now we have to consider such an element, T belonging to this group, and of course it means that we have to distinguish between right translation and left translation. Okay, so here it was right translation, but we also have left translation. Okay, and as this group is non-commutative, these two things are distinct one from the other. So here, what is the formula we get? So we have to be a little careful. Once again, we can deduce the formula by a change of variable, a formal change of variable in the defining formula. So what do we get? We get that the Fourier transform of a function h translated on the right by t is the Fourier transform of h translated on the left by t minus 1. And here there is a correcting factor. We have to take the determinant of t and then the same norm as before to the power minus 1. Okay, so here the norm I write is the same idea as before. Okay, it goes from A cross to R plus cross. So it is the same as before. It is the character through which the group X cross acts on additive measures on A. Let me be careful. No, here I am. You see, I am making a mistake. It is minus r, so I have to be. Yes, it is minus r because the space we are considering has dimension r to the square. So here is the correct formula. And then we also have the Fourier transform of left translates. So, of course, you can get the correct formula. You have the same corrective factor times the Fourier transform of h translated on the other side, here on the right, by t minus 1. So this is the correct formula. Okay. By now, we would want to define, once again, small spaces, not, you see, of course, we have the space of square integral.
So your idea is basically the path integral, but slightly specific path integral, right?
No, you should stop asking those meaningless questions. You can continue.
Okay, so it is possible to define small spaces of very regular functions, which are once again small and stable under the Fourier transform, unstable under multiplicative translation. So here, of course, when I say multiplicative translation, I mean both translations on the right and translations on the left. So, so here the simplest case to consider is the case of functions on non-Archimedean local fields. So, in fact, here a natural space is the space of functions defined here, which are, once again, which have compact support and which are locally constant, exactly as before. And here there is an analog of that in the case of R, of C, built just as before on the definition of the Gauss functions. Anyway, at all places, and also in the global case of the Hadel ring, it is possible to define small spaces of regular functions which are stable under the Fourier transform, the multiplicative translations on the right and on the left, and also invariant differential operators and possibly other operators. Okay, so we have these small spaces. And lastly, the last thing we have is, the most important, the deepest result, is the fact that we still have a Poisson formula. So, how is it written? So, exactly the same as before. Here I replace z by mr of z. So, this is the case when r equals A equals R, so this means I am considering functions on MR of R with values in C, which are very regular in some sense. And here I am considering the evaluation of this function h or its Fourier transform at the integral numbers. And here I can do the same in the global case. So here I replace the summation over f by the summation over mr of f. And the formula we get is still valid So the evaluation of this discrete subgroup of matrices is the same for any H and its Fourier transform. Okay, and so we can do the same as before, which means to consider this formula and to let the group GLR of AF act on it. So it acts on it both on the right and on the left. And if you let this group act here on the right, it will act there on the left. If you make it act here on the left, it acts here on the right, okay, through the formula I have written there. And once again, you can decompose spectrally this identity. You say, well, you are just in the space of distributions, and you have a special distribution which is preserved by, which is fixed by the Fourier transform operator, and you just decompose this vector spectrally. So you write, if you want, you write you decompose the space of distributions under the double action of this group on the right and on the left. And you get identities between the components in the irreducible factors. And in this way, what you get is the usual properties of global L functions for automorphic representations of linear groups, GLR. Okay? In fact, I should stress the fact that once again, in that case, this whole story I have said is equivalent to the possibility to define the L functions first locally, because yes, I should say that for number theorists here, that the definition of the so-called local factors of L functions is equivalent to the definition of these small spaces of regular functions. To be able to define these small spaces of regular functions is the same as to be able to define the L functions. And to be able to define the Fourier transform operator is the same as to be able to define the local gamma factors of automorphic representations. So why is it the case? It is the case everything we are saying is stable under right and left translation. So it can be decomposed spectrally. So for instance, 4.3, I have a space of functions, of so-called very regular functions, which is in particular stable under multiplicative translation on the right and on the left. So for general spectral reasons, it can be written as a sum of components according to the depending on the different irreducible representations of the group. And when you write what it means concretely, you see that you can characterize this, the functions belonging to these small spaces by some datum which appears and which is called the local factors of global L functions. The Fourier transform itself is stable and is compatible with right and left translation, so it can be decomposed spectrally, and it means that on every irreducible space under the action, under the double action of GLR, it has to act by a single eigenvalue because of the Schur lemma. And this eigenvalue is the so-called gamma factor of number theory. So you have the definition of the L functions because of the existence of such spaces. You have the definition of the gamma factors because the Fourier transform is compatible with translation on the right and on the left. And here already you have the definition of the L factor, so of the L function as a product of all possible L factors. You have a definition of the gamma factors, so of the so-called epsilon factors. And lastly, you have the Poisson formula, and in this whole story, the Poisson formula is not only a consequence, but it is equivalent to the fact that the L functions, the global L functions, verify analytic continuation and functional equation. Okay. Okay, so by now I want to come to some commutative, non-additive setting, always for this formula. So, in order to do that, I want to do the following. First, I will come back a little because I will come back to the commutative setting. So, commutative, I remind you, was it referred to the case where we did not have here, we had here R equals 1. So this means that the group is A cross. But of course it is possible to replace A cross, which is a commutative group, by an arbitrary power of A cross. So what does it mean? It means that I am to considering A cross to some arbitrary power R embedded into A to the power R. Okay? And here, of course, I have something which I can still close a trace, which goes to n. It's just the sum of the different factors. And here, I have the character psi to the circle S1. And here, what I can do is to repeat once again the whole story with the A we had at the beginning replaced by A to the power R. Okay, A to the power R, of course, is a ring. So here I have that. Okay, so I just replace with AR. Here with AR. Instead of GLR, I have A cross to the power R. Okay, acting on the right and on the left, but here, because the multiplication is commutative, it is the same. And here, yes, I have the determinant to the power -1. So what is the determinant? The determinant from A cross to the power R to A cross is just the product of the R different factors. So I have this, I have a definition of small spaces built always in the same way. So here I replace MR of fx with fx to the power R. And here I have z to the power R, z to the power R. And here, f to the power r, and f to the power r. Okay, and here I let the group which acts is just af cross to the power r. And here I am considering a function h on af to the power r. Okay, so I do this. And in fact, in this part 3, what I want to do is to forget addition. So, here you observe something, which is the fact that I am considering functions. On A to the power R with values in C. But of course, in A to the power R, there is an embedding of A cross to the power R, and this is dense here. So this means that if I am interested in square integrable functions, it is the same to consider them here or there. Okay? So this means that for the definition of the Fourier transform, I could just as well write, consider functions on A cross to the power R. Of course, here there is an implicit use of addition because I am considering a measure which is invariant with respect to addition. Okay, but at least in the definition, for the function h and its Fourier transform, I can consider them as functions on the group. Here, for the small spaces of very regular functions, as these functions are very regular, it is the same to consider them on A to the power R on A cross to the power R. The space of functions I am considering are just spaces of function on F cross to the power R which extend by continuity to a to the power r, such that to become very regular. The only thing where it seems I really need to consider the continuation is the Poisson formula. Because in the Poisson formula, we cannot restrict the summation to the multiplicative numbers. We have to consider we have to consider 0, for instance. Okay? Okay, so you do that, but by now, what we would want to do by making use of multiplication is to take a quotient. Okay, so what does it mean? It means that we consider the torus, which is implicit behind this writing, so gm to the power r, together with the determinant morphism, okay, which goes to gm. And what we would want is to consider a quotient, so an arbitrary torus, which is a quotient of gm to the power r by some kernel, which I write in this way. A kernel T-row of gm to the power r. And the only requirement I want is the fact that the determinant homomorphism from gm to the power r to gm, which is just the multiplication of the coordinates, I want it to factorize through t. Okay, so this means that here I want a character which I write det t, which just factorizes. So in other words, I want the kernel, the subtorus of gm to the power r. I choose here to be embedded into the kernel of the determinant morphism. So this is my only requirement. And by now, what I can do is to take the definition of the Fourier transform and to make it invariant under the action of this group. Okay, so I just consider such writings, and what I do when I am, for instance, at a local place is to consider the following. So I have gm to the power r evaluated at fx, which is fx cross to the power r, and here I have a natural morphism to t of fx. Okay, so I have this morphism. So in general, this homomorphism will not be surjective, but its image will always be an open subgroup. Okay, so on the kernel of this map is T-row. The kernel is T-row of fx. Okay, so here it is always exactly that. And so what you can do is to choose an invariant measure on T-row of fx and then to integrate. So what does it mean? It means that you consider this map from fx cross to the power r to t of fx. So here you have rho, and there is an induced map, which I call the direct image map. It associates to any function h on fx cross to the power r with values in C. It associates its direct image. So this is a function on t of fx with values in C, which is defined by integration along the fibers, according to the invariant measure we choose. Okay, so maybe I should write the correct formula. So this is the integral over t rho, let's say over rho minus 1 of t with respect to some invariant measure on the kernel of h evaluated at t rho. Okay, so this is the direct image formula. And what do I want for the Fourier transform? I want the following property to be verified. I want the direct image of Fourier transform to be the Fourier transform of the direct image. Okay, so and I can define the Fourier transform on the quotient, which means the Fourier transform on t of fx by this formula. Okay,
And of course, here you will tell me it is only defined on the open subgroup, which is the image of this map, but it can be extended on the whole group by requiring that these formula are still valid. Okay, here you replace det by det t, and it is still okay. You have a unique Fourier transform which verifies both this formula and compatibility with translation. Here, right and left translation are the same because you are on a commutative group. So, and by now, property 1 is still valid. It means you have a unitary operator. So by now it is defined on T of A, okay, local or global, and it indeed uses an automorphism of square integrable functions. Okay, so it is compatible with translation. Then it is possible to define small spaces of very regular functions. So how are they defined? Just by taking the images by this operator, rho lower star, of the small spaces of very regular functions we had on A cross to the power R. We just take the direct images. So here I have to stress the fact that these very regular functions on the quotient we get by integration do not extend by continuity to some bigger space where they would be continuous, smooth, anything you have. They do not extend. The definition of very regular function is just the fact that they come from the spaces we had before by taking the quotient. Okay, and lastly, here it is a fact, in fact, it is a very non-trivial fact, that the Poisson formula can still be written in that case. So, well, of course, it does not anymore have this form, because once again, it is not possible to extend this function. So here, what is the form of the Poisson formula? It is the fact that it is possible to define on these spaces of very regular functions a linear functional, a linear form, which is fixed by the Fourier transform, and which is, in some sense, is a quotient of the Poisson linear functional we had in the additive case. Okay, so we are no more in an additive case. We don't have any more continuation of these very regular functions on the boundary, but it is still possible to define a Poisson formula, which means a Poisson linear functional stable under the Fourier transform. And once again, you can do all the usual stuff, which is to let the multiplicative group T of AF, T of the Adel ring, act on this formula. You decompose it spectrally, and what you get is the properties of automorphic characters of this torus, which is no more, you see, this torus does not come anymore from an additive structure. So, okay, so what you are considering for a number theorist here is just the L functions of this torus T endowed with this morphism from Gm to the power R to T, which of course can be seen as the dual of some morphism from the dual torus of T to the dual torus of Gm to the power R, which is C cross to the power R. So here I am talking for number theories. So here, this of course would be the datum considered by Langlands. Okay, so this whole story, once again, can be written here. Here there is a real result, which is the fact, the only real result is the fact that the Poisson linear functional can be defined in purely multiplicative terms, which was not the initial definition. Okay, so you may ask also about what here I just said that it is possible to give a purely multiplicative definition of the Poisson linear functional. And you may ask, is it also the case when you consider the non-commutative case, which means the case of matrices GLR embedded into MR? And the answer is yes. So in that case, in fact, you can tell the whole story. So this is exactly the same story. You consider exactly the same objects, but everything can be said in purely multiplicative terms. Which, in fact, I think it is by now quite. In fact, it is a theme which has appeared in mathematics at several places in the last years or decades. The fact that, in some sense, multiplication is a more important operation than addition. And here, you see the Fourier transform and the Poisson formula especially was defined with respect to the additive structure. So this means that you were considering an embedding of the space, of a multiplicative space in an additive space. At first sight, you may think you had definition of this, your definition needed the additive structure, but eventually it does not, and everything can be said multiplicatively. And by now, of course, what we would want to do for the last 5 minutes is to consider the non-commutative, non-additive Fourier transform. So what does it mean? It means the following. So you see, before, first we had GM embedded into the additive group A1, and then we consider GLR embedded into MR, and then we consider the torus TR, which is GM to the power R, together with a quotient T, a quotient torus. So there was an additive structure here, but no additive structure there. And of course, at first sight, what we would want to do is to combine that and to consider an arbitrary linear group, and then the first naive idea would be to consider a reductive group here, which would be a quotient of GLR. But this is not interesting because there are almost no quotients of GLR. The only quotient of GLR is either there is GLR, there is a PGLR, there is GM, and that's all. Okay, you don't have intermediate quotient. So the genius idea of Langlands is the following. So instead of considering here a morphism from TR to T, what you consider is you consider the same as an homomorphism between the dual groups. And it has the advantage that it goes in the other direction. So the dual toruses are complex toruses, and to consider such a morphism from TR to T is the same as to consider such a morphism from the dual torus of T to the dual torus of TR, considered as the torus over C, so it is just C cross to the power R. And then what Langlands does is not to consider this thing, which is not interesting, but to consider a morphism from the dual group of the reductive group G, which is a reductive group over the complex number, together with some morphism to the dual group of GLR, which is GLR of C. So in other words, what you are considering is an arbitrary representation ρ of the dual group of G. And here, this situation is completely non-trivial, and it is very rich because there are infinitely many different representations of the dual group. And so Langlands has predicted that for such a datum, we should be able to tell the same story as what we have said here. So what so here, of course, Langlands did not state it in this way, but it can be proved that what Langlands has predicted is equivalent to the fact that everything I have said can be generalized in this situation for an arbitrary ρ. So this means that first we should be able to define an arbitrary Fourier transform. You see, I call that the ρ Fourier transform. So for such a ρ from G hat to GLR hat, so this thing should define a raw Fourier transform on G of fx of G of the Adel ring, and you see that for any single reductive group, there should not be only one Fourier transform, but a whole family, an infinite family. There should exist as many Fourier transforms as there are representations of the dual group of G. So this is an extremely rich situation. So this is the prediction of Langlands, and so under the name functoriality. But it can be proved that it is equivalent, that this whole story should be true. So the raw Fourier transform should be unitary. It should induce an automorphism of square integrable functions. Okay? It should be compatible with right and left translation with respect to some formulas here. So here we would have to replace the characters we had by some character of the reductive group. We should be able to define small spaces of very regular functions which are stable under the Fourier transform and under multiplicative translation. And lastly, there should exist a Poisson formula, which means a Poisson linear functional fixed by the Fourier transform operator. So, maybe I take 2 minutes for finishing. Because this was the point I wanted to stress, to introduce. Here, you see the first problem is the definition. The definition of a Fourier transform operator. And if you come back to what I have explained so far, you see that at first I had written a formula, which was the definition of the Fourier transform in the usual case. And this formula I had written there, in some sense, is the same everywhere. Because we consider, for any possible A, we consider an additive measure, we consider an additive character. So in some sense, it is the same at all places. But by now, we are no more in an additive setting, because we don't have any more additive structure. So we don't have the notion of additive measure, and we cannot consider an additive character. So we need to express the fact that the definition of the Fourier transform is the same at all places. We need to define it in another way. And then the idea you may possibly have is the following. You can consider the Fourier transform of pointwise multiplication of functions. So this, in the classical additive case, is, of course, the convolution operators with respect to addition. And by now, if you look at the formula for the expression of the convolution operator, you see this formula has a very remarkable character. It is completely algebraic. You see, in this formula, there is no more character psi. The problem with psi is that it is not algebraic. It is an exponential, for instance, in the case of R or C. So you don't know, it is not easy to understand what is the analog of an exponential in the p-adic case. But when you consider the convolution operator, it is algebraic, and it is the same at all places. It is exactly the same. And this, you may dream to generalize in an arbitrary setting. And in fact, you can prove that in the different cases I considered, part 1, 2, and 3, the convolution product, always defined as the Fourier transform of pointwise multiplication, is always algebraic. And you may wonder, is it the case? Can we expect the Fourier transform operator to be algebraic in general, which means for any row? And so, in fact, I have worked on this for, in fact, quite many years. But in the last months, I think that by now I have not a full solution to this problem, but at least a partial solution. And in fact, the answer is the fact that this partial solution of this problem, the fact that the convolution operator is algebraic, at least in a restricted sense, is enough to determine it completely. So by now, I think I have these properties. So in fact, at least it is possible to give a general definition of the Fourier transform in this arbitrary setting, just because of this algebraic property, not as strong as what I already said. It would be required. It is more technical, but at least I have a definition. So I have a I also have a definition of the smaller spaces, and of course, what is missing is the deepest statement, which is the statement which is a proof of the Poisson formula. I also have a definition for the linear functional, but so far I was not able to prove the Poisson formula. So, okay, so excuse me for talking a little too long. And, what I wanted to say is to tell this story in, you see, in the purely analysis terms, because I think it is quite interesting. And when I talk to a general audience, I always try to make people in analysis interested to this subject, because you see that people hear about the Langlands, and so they are a little afraid. This is automorphic, this is very complicated. But it can also be considered as a problem in analysis. And for instance, this Fourier transform operator associated to these representations in particular exists for reductive groups with values in R or C. So here we are really in analysis. So you see that in analysis there is not only one Fourier transform operator, as we are used to, but infinitely many of them. And I really don't know whether it can be useful in analysis or not. For sure, in number theory, it is very important. So, okay, thank you.
Are there any questions, comments?
So can you apply your more, if you fine-tune more into the more advanced level, can you apply your Poisson type distribution to the some sort of string theory, or
I don't know. No, I don't know at all. I am trying to approach the Langlands program. You see here with the purely analysis tools, whereas of course many people here know that the Langlands program can also be approached through algebraic geometry tools, especially the study of so-called Shimura varieties. And so this is, in fact, it is quite fascinating that you have the same statement which can be approached both through purely algebraic geometry terms, or the other through, so this everything I have said is in harmonic analysis, and there is no geometry. But this is the same statement which can be approached in these different terms. And, so I really wonder whether it can have ramifications in other fields. And I would be interested, in fact, in a point of view by people working in analysis about that.
I have a question, maybe very vague question. So there are two worlds in number theory, so number fields and function fields.
Yes.
So in the function field setting, do you think both stories
Yeah,
are parallel, or?
So your question is very good. Of course, everything I have said makes sense both in the case of number fields and in the case of function fields. In the case of function fields, by now we know the automorphic transfer of Langlands from an arbitrary group to GLR, thanks to the combined work of Drinfeld, myself, and my brother, more recently. So we know the automorphic transfer, and so as a consequence, we know that everything I have said in Fourier analysis terms is true, which means not only we know there exists a Fourier transform and so on, but most importantly, we know the Poisson formula. But you see that the proof of that is extremely indirect, because it uses this very complicated algebraic geometry. So you see the study of so-called Drinfeld moduli space of Stukas, which are the analogs of Shimura varieties. or in the work of my brother, you also have not only analytic geometry, but perverse sheaves, so the so-called tools from the so-called geometric Langlands program. So this is extremely sophisticated algebraic geometry. And eventually, all of this allows to prove a statement which is not so difficult to state in harmonic analysis. And so, of course, I would want a direct proof, but so far I am not able to give it even in the function field case. So far, in the function field case, we know the formula is true, but we don't know to prove it by purely analytic analysis means.
Any more questions? If not, let's thank the speaker again.